probably today. Okay, so let's talk about equilibrium before we come back to that sort of simulation, because I think the visual is very helpful to keep in mind that you get these things flowing back and forth, you change concentrations, it's the balance that stays the same, which is kind of the magic of equilibrium and K. So kind of looking at where we are at in a progression of things, we talked about in the last chapter, speed of reaction, the rate of reaction, what determines the rate of a reaction, and mostly thinking about that just in a single forward direction. How do the reactants affect that rate of reaction? How does the mechanism of the reaction affect the rate of reaction? In this chapter, we're going to talk about equilibrium, which is the extent of a reaction. So a lot of the reactions that you do in general chemistry, especially Chem 1 or Chem 20, are specifically picked because they go almost 100%. So like Chem 1 actually recently did the potassium iodide lab. You use way more, or zinc iodide. Use way more zinc in that lab than you need. Because you're overloading the one reactant so much, it pushes that reaction almost to 100%. So you can get a good result in terms of that's the empirical formula calculating how many iodines per zinc. But most of the time it doesn't go to 100%. So how do we know how far the reaction goes? That's equilibrium. And we'll look at K, and then I think I had on this. Next slide, in the next chapter, we'll start talking about acids and bases. So we'll take rate and equilibrium, and we'll use those two and say, like, how can we use these sort of practically to do calculations for different chemical reactions? And then eventually we'll get to thermodynamics, where we'll talk about why is the equilibrium what it is for a certain reaction? Why is it that a reaction stops at a particular ratio of reactants to products and always stops at that ratio? The equilibrium constant is an experimentally measurable quantity used to define or quantify how far a reaction goes. And it's different from the rate constant because it's a capital K. Rate constant's lowercase k. And it's different from Kelvin, as the book says, because it's italicized. You can't really write in italics. But most of the time context will tell you if it's Kelvin or if it's a rate constant. K is greater than 1. If K is greater, well, we haven't talked about Q yet. Oh, no. Sorry, getting ahead of things. K is greater than 1, that means that there's more products than there are reactants at equilibrium, meaning that the ratio favors products. And actually, if I go back to this, look, K is 10. What's favored? Products. And in this, such a simple reaction, I've got A, I've got the black, turns into red. It's very, very simple. And so we can do really easily, there's 10 times as many red dots as there are black dots. Ratios get a little bit more complicated when we've got multiple reactants or multiple products. But for something like this, our K is 10, meaning I'm always going to have 10 times as many products as I do reactants. If I add more reactants in, then the reaction rate for the reactants will pick up until it's back to that ratio of 10 to 1. So when we say that this is an experimentally measurable quantity, we can measure at equilibrium the concentrations or pressures of the reactants and the products and get a ratio. If K is less than 1, then my denominator would be larger than my numerator, and you get a number less than 1, so I'm going to have more reactants than products. 1 would be equal. Bless you. So really, this is where, actually, I'll reset this. And we won't do, actually, let me change the rate. Let's make it 5. So if I start with only reactants, as the reaction proceeds, as we learned in the previous chapter, the concentration decreases, which means the rate decreases, and we could now do first order, second order, zero order. This should follow some first order. Because it's so simple, we could say that the mechanism is the same. So you can see the rate decreasing, ending up at 35 reactions per second. And the rate of the products will keep speeding up until it matches the rate of the reverse. So they end up meeting. And as we saw in the last chapter, our reaction rates generally increase with increasing concentration. So our reverse reaction, which we only mentioned super briefly, but is the reason for the double arrow, the reverse reaction picks up in speed as the concentration of the products increases. Not all reactions are reversible. But in this case, we do have a reversible reaction. So dynamic equilibrium is that special state where we have a forward reaction that continues to happen and a reverse reaction that continues to happen, but they do so at the same rate. And so the relative concentrations, the ratio between them, never changes. They both still occur. The concentrations don't change relative to each other. They don't change either. Because anything that gets removed from one side gets replaced as soon as it's removed. They are almost never equal to one another. Almost never. So if you think about all of the possible situations, there's an infinite number of possibilities where one is greater than the other. There is one possible situation where they are the same. So almost never happens. It's not that it can't be equal to 1, it just almost never is. And the relative concentrations will depend on the value of the equilibrium constant, and then the equilibrium constant is determined by other thermodynamic things that we'll talk about later. So which statement does not generally apply to a chemical reaction in a dynamic equilibrium? Yeah. So rates of forward and reverse reactions are equal. That does occur for every reaction at equilibrium. The concentrations of the reactant products are constant. That's true. So C is where it is not generally true, where they are equal to 1. The equilibrium constant is deceptively simple to calculate. And we can actually just come up with an equation from our balanced chemical equation to calculate K. So in the simplest situation, it's products divided by reactants. And that is the ratio of products to reactants that the reaction will eventually settle at, because those are the concentrations necessary for the forward and reverse reactions to be the same rate. So even if you bump it, if I take this reaction and I add some more over here, I've disturbed that. Now you see the top, the K says 1.28 because it's calculating the K. But I've got, actually if I go a little bit more, right, my reactants and products are now almost equal. We saw before, this reaction is not going to settle at equal concentrations. So once, quote unquote, disturbed, I've now increased the rate of one reaction by increasing the concentrations. And so that reaction is now too fast. And so now some of those reactants get turned into products, or I could disturb the products. And as that reaction proceeds, then it will shift back towards the reactants. So that's like Le Chatelier's principle. Add something to one side, it will shift towards the other side. If you remove something, which I can't do in the simulation, then it would shift towards what you removed, but it's always shifting so that the ratio ends up the same again. So if the ratio is supposed to be 10 times as many products as reactants, if I add reactants, now it's not 10 to 1. And so it'll shift. So the reactants decrease, the products increase, and it gets back to that 10 to 1, or whatever it happens to be. Now when we add coefficients, it doesn't really add that much to this. So it's the concentrations of the products raised to their coefficients divided by concentrations of reactants raised to their coefficients. Because K is the ratio of the concentrations of products divided by the concentrations of reactants. So where the rate constant, lowercase k, can only be determined experimentally because there could be other mechanisms going on, and we can't even just write a rate law from the balanced chemical equation. Since the equilibrium constant is just talking about the measurable quantity of what is the concentration of the product, what is the concentration of the reactant, we can come up with an equation to calculate K for any chemical equation. We'd have to do the experiment still to figure out what exactly K is in terms of what number is K. What is that ratio going to be? But this is the equation. And it's called the law of mass action. So according to the law of mass action, or if we wrote an equation for the equilibrium constant, what would that be for this reaction? D. Because we're taking C, concentration of C, which is my product, raised to the coefficient 3. A raised to the second, B the first. Easy. So if we apply the law of mass action to this equation, right, again, our coefficients become those exponents. And give us an equation where we could find what K is. So if we want to express the equilibrium constant, or an expression that will give us the equilibrium constant, capital K equals what goes in the numerator? Products. Yep. CO2 to the 3 times H2O to the 4 C3H8 to the 1 O2 to the 5. We're fifth. Yeah. We'll get to that later. Because like, yeah, in this case of solubility, You got to think about the things that are available to react. So it can be slightly different. No. We haven't gotten there yet.
So as of right now, do not include states. We will get there.
Well, yeah, in a solid or liquid, we usually ignore water because if it's part of the reactants or part of the products and it's in an aqueous solution, it's kind of on both sides, and so we ignore it. If it's a solid, then it's not actually in the solution, so we can't use the molar concentration, and so it doesn't get included. Again, later. So far, everything's going to be included for now. Oh, this we've already kind of covered. So what happens when you add more reactants to a dynamic equilibrium? If I add, so K is the constant. So K will always be the same thing. And the equation, the book talks about Q later. So there's at equilibrium, that's where the ratio is K. When you're not at equilibrium, we would call that ratio Q. So if I disturb this equilibrium and I add reactants, like this does calculate it on the fly, so it will just change K there. Really what that is now is Q. We know that, well, actually I don't remember, what was the K? I don't remember what it said before. 25? Yeah, so the K wants to be, so now we're at 2, it wants to be 25, and so it's going to shift to get back to 25. And that means that I have to decrease my concentration of reactants, increase the concentration of products. Which is why we say it shifts towards the products. And so we shift. At this point, I should pick a ratio that goes faster even. So there's actually several things that happen. So we could say that the reaction, in terms of like Chem 20, maybe Chem 1, Le Chatelier's principle, shifts toward, that's a weird W, products. But a little deeper, how does it shift towards the products? What about the reaction changes that causes it to shift towards the products? The ratio's off, so we need to the right ratio, or the rate. So if I add more reactants, I increase the rate of the forward reaction. So initially, I just increased the rate of the forward reaction. I just dumped all of this extra reactant in. But over time, does the rate of the reverse reaction stay the same? It also increases. Because as I start turning those reactants into products, now the rate of my, or the concentration of my products is increasing. But it'll increase over time, and the reaction of the forward will start high and then it'll slow down again. And eventually they meet in the middle. And actually, I have that on here also. If we toggle the graph and I add a bunch more over here, these are the reaction rates. So the rate, the black line is the rate of the reaction rate of the reactants. So you can see as soon as I go forward one step, that spikes, but it'll start to come down over time. The rate of the red comes up just a little bit. Doesn't need to move much until they end up as the same thing again. So anytime you disturb the reaction, the rates all increase, but the forward rate increases a lot and then slows down. The reverse rate will increase until it gets back to equilibrium. So what happens when you add more products to a dynamic equilibrium? Yeah, the reaction shifts towards the reactants and say that we increase the rate of the reverse. So we could talk about, and we often do this in chemistry, is we personify reactions, we personify chemicals. What do they want? Ultimately, what they want is to be in the lowest energy state possible. But it helps to think about them in this way. So when we say like the reaction wants to get back to K, it wants to get back to that ratio, it's not so much about wants, it's more about you gave it a push and it swings back to that ratio. So because you gave it a shove, you threw off the balance, it starts a whole cascade of things that eventually bring it back to that equilibrium, which would be the lowest energy state. So any system, dynamic equilibrium, if it is a reversible reaction, will return to that equilibrium when disturbed. Like that's what you're doing in lab this week. Already did if you had lab yesterday, will do if you have lab on Friday, is you're taking those chemical reactions, you're basically setting up a dynamic equilibrium as soon as you mix things, and then you are disturbing it by adding more of something and shifting the, you're not changing where it ends up as at the dynamic equilibrium. There must be other mechanisms, other things that shift. Changes in H3O plus because you're moving other things, which cause indicators to change colors. That is the point of the lab, though, is to disturb an equilibrium and watch it shift from one side to the other. So increasing reactants or product concentrations will increase the reaction rate, or if you decrease them, you can decrease the reaction rate. And then rates will increase until they're the same. So we said when K is large, or a lot greater than 1, greater than 1, the numerator is larger than the denominator and the forward reaction is favored. In like a chemical engineering standpoint or in a production chemistry standpoint, you want large K because you want to make as much product as possible. So if you can consume all of your reactants, that's a more favorable reaction. So like this reaction, and a lot of rates are going to be in scientific notation, so 10 to the 19 rather than 25 in the simulation. If you have a very small K, much less than 1, it indicates that that reaction doesn't go forward very much. And so you're going to have a hard time getting products out of that reaction. What would happen, though, if I reversed this reaction? So if instead of taking nitrogen and oxygen gas and making nitrogen monoxide, what if I wanted to take nitrogen monoxide and turn it into nitrogen and oxygen gas? What would K be for the reverse? Kinda. How do we calculate K? We say for the forward, it would be, we can call this K1. Right, it's the concentration of the products divided by reactants. So if I flip that reaction around, what happens to K? It inverses. So if I want to know what K is going in the other direction, so -1, this is now the concentration of N2 times O2 divided by NO squared. Or I could take this K and raise it to the -1. So when you reverse the reaction, you flip the equation and you flip the K. So this reaction is very unfavorable as written. If we take the reaction and reverse it, it would be very favorable in the reverse direction. Or we would have a much higher concentration of reactants versus products. Oh, right. But this says nothing about how fast the reaction happens. It just tells us when it's going to not stop, but it tells us what the ending concentrations are going to be. It might get there very, very slowly. And if it gets there very, very slowly, then even though this is very favorable towards nitrogen and oxygen, if it does so very slowly, it's going to take a long, long time to get to that equilibrium. Which is why we have the separate study of kinetics. So small k, reverse reactions favored, k equals 1. Neither direction is favored, you get about halfway. Forward k is, or larger k favors the products. Talk about it later, but temperature, K is dependent on temperature. So at which temperature is the equilibrium constant the largest? Large K means we favor the products. In this case, the products are the black circles. So this one's got, was that 1, 2, 3, 4, 5, 6, 7, 8 over 2, so 4. So in this one, we're given an equilibrium constant, which is 10. And then we have initial concentrations of A and B. So we have reactants, but no products. What would the concentrations be at equilibrium? K equals 10, which is equal to the reaction, or concentration of the products divided by the concentration of the reactants. So could it be C? No. Can't be C. Because if the concentrations were the same, K would be 1. So then which of these equals 10? One divided by 0.1 or 0.1 divided by 1? Does that equal 10? Nope. Process of elimination. Or calculator. So it's B. All right, so we actually talked about this one already. So what would the equation for K for the forward reaction be? Mm-hmm. Over A over B squared. If we reverse the reaction, reverse the equation for K. So now it's the concentration of A times B squared, concentration of C cubed. All right, so we could even write out sort of a K for the forward equals, yeah, 1 over K reverse. So you just inverse it. But what if you multiply coefficients by a factor? Something like, right, in Chem 1 you do Hess's law, add the equations together, the fact that a series of steps is equal to the same amount of energy as all of the steps combined. You take those reactions, you reverse them, add them together, multiply by coefficients, cancel things out. You can use standard heats. I know some of that's in Chem 1. That's why you would want to do all of this. So again, we have the same equation. If we just have C to the 3, A, B to the second. If we modify our equation and multiply every coefficient by some factor, this would be C, and then this is, no, it is C, it is just 3N. A to the N, B to the 2N. Because really we're taking the whole thing and we're raising everything to the same power. So if you put a 2 in for N, then it's everything squared. But if you take x to the 3, and you square that, then it becomes x to the 3 times 2, or x to the 6. And we can also add two equations together. When you add equations together, you multiply their equilibrium constant equations. So this would be K1 times K2 b squared over a times c cubed over b squared. So then these cancel out, and the rate of the overall what's another way you could get to that same answer? Yeah, kind of like we talked about reaction mechanisms. If I actually add these equations together, 2b cancels out because it's a react a product. And the equation that chemical reaction I end up with is A equilibrium 3c, which matches the equilibrium expression that I just wrote. So if I take this reaction and I modify it, so we're going from A becomes 2b, 2b becomes 1/2 A. I know that K for this first reaction is 0.010. What is K for the new reaction? Probably. So we gotta reverse this. Do we think of like, how do I get from here to here? So how do I get from here to here? I don't know, I can't even do it in my head. So reverse the reaction, so that means I need to take my K and I'm gonna raise it to the -1. So that's the reverse. But then I also do something to the coefficients. Divided the coefficients by 2. So if this was, well, for A it was 1, for B it's 2. If I take that and I divide it by 2, so this would have been really 1 times 1/2, 2 times 1/2. Sorry, I'm trying to relate this back to, let's go back up to this one. So the factor that we raise all of the, or that we multiplied or divided all of these by, if that's n, or like here, 2n, in the one that we're doing, the n is what we're trying to find. So if this is 1n and this is 2n, how do I get to 1/2 and 1? Multiply by 1/2. Because then when our exponent up here is now times 1/2. And so our final K should be whatever 0.01 raised to the -1/2. So it's B. The half is kind of tricky. I think there's another Yeah, we've got to factor in that one too. Let's look at this last one real quick. Are there any questions so far? Okay. So consider the following chemical equation, and we're given an equilibrium constant. They've manipulated that chemical equation and want to know what's the new equilibrium constant. So maybe we should start by, how has the chemical equation itself been manipulated? It's reversed. So we've reversed it. So it'll be k to the negative 1. You say divided by 2? Multiplied by 2. Multiplied by 2. Oops. So if it's multiplied by 2, what do we do to k? Yeah, and we can think about this in steps. So we could even take k and then do the inverse. And after we do that, we can take k and we would raise it to the second. Because if I multiply all of the coefficients, I'm multiplying the number that everything is raised to, all of my concentrations. So I'm really squaring or raising k to whatever power I multiplied everything by. So this should be, and then we can take our k, we could combine those. We could say k is 2.2 times 10 to the negative, or times 10 to the 6. I need to raise that to the negative 1, so now it's, oh, it's not going to be 2.2. Not so simple. Raise to the negative 1, and then we need to square that. So this is 2.0, well, actually 2.1 times 10 to the negative 13. Questions about how? I think parts of this, well, my theory is that parts of this, because I remember this was not necessarily this part, but writing out the equation for k, well, maybe I'm thinking of Chem 20, but was one of the things that people tend to miss. Sorry, almost had to sneeze. And I think it's just because at first it seems really simple, and then you don't do enough practice because it seems simple, because it seems straightforward. But I'll assign problems on Alex so that you can practice these. And yeah, should have the exam graded definitely by Friday. And we'll keep talking about equilibrium on Friday.